All right, so we're going to be working on Chapter 8, Lesson 1, Multiplying Monomials. What you're going to learn about is how to multiply monomials and how to simplify expressions involving powers of monomials. Some vocabulary to keep in mind are what is a monomial and what is a constant. Why does doubling speed quadruple braking distance? So the table shows the braking distance for a vehicle at certain speeds. If s represents the speed in miles per hour, then the approximate number of feet that the driver must apply the brakes is 1/20th s squared. Notice that when speed is doubled, the braking distance is quadrupled. So this is an example of what a monomial is. So multiplying monomials. An expression like 1/20th s squared is called a monomial. A monomial is a number, a variable, or a product of a number and one or more variables. An expression involving the division of variables is not a monomial. Monomials that are real numbers are called constants. So notice how this one does have division, but it's just 1 divided by 20, where it says that monomials don't include or involve division of variables. So if there was a variable in the denominator, right in the bottom of a fraction, then it wouldn't be a monomial. But this one is. So, identifying monomials. Determine whether each expression is a monomial and explain your reasoning. So, for -5, is that a monomial? The answer is yes. And the reason why it's a monomial is -5 is a real number and an example of a constant. A constant just means it has no variables, but it's still considered a monomial because it's just a number. Is p plus q a monomial? The answer is no. And the reason why it's not a monomial is because the expression involves addition. Monomials only involve multiplication. Is x a monomial? Yes, it is a monomial, right? It's just a single variable. Single variables are also considered monomials, right? Just like a single number is considered a monomial, a single variable is also considered a monomial. C over D. Is this a monomial? The answer is no, it's not. And why? Because the expression is a quotient. It is a division, right? Not a product. It is a division, and we're dividing by a variable. So therefore, it is not a monomial. Is a, b, c to the eighth over 5 a monomial? The answer is yes, because I'm just multiplying a bunch of variables together and I'm dividing by a number. I'm not dividing by a variable, right? So the expression is a monomial. So here's another way that they expressed it. They rewrote it as instead of dividing by 5, it's multiplying by 1/5. So this expression is a product of a number 1/5 and 3 variables. So recall that an expression in the form x to the nth power is called a power and represents the product you obtain when x is used as a factor n times. So the number x is the base and the number n is the exponent. So again, if we had 2 to the 5th power, 2 would be considered the base and 5 would be considered the exponent. So if we were to do 2 to the 5th and expand it out, write it in expanded form, it would just mean that I would do 2 times itself 5 times, right? I would have 5 factors of the number 2. And if I were to multiply that out, that would be equal to 32, right? So 2 to the 5th power means 2 times itself 5 times, which just equals 32. In the following examples, the definition of a power is used to find the products of powers. Look for a pattern in the exponents. So here I have 2 to the 3rd power times 2 to the 5th power. So if I were to rewrite this in expanded form, kind of like how I did up here, I would write it as 2 times 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 2, right? Here I have my 3 factors of 2 from 2 to the 3rd power. And here I have 5 factors of 2 from 2 to the 5th power, which is a total of 3 plus 5. It's a total of 8 factors of 2. So if I were to rewrite this with an exponent, I could rewrite it as 2 to the 8th power. And if you look, do you see any pattern between this expression and this expression? Look at the expression we started with and look at the expression we ended with. You can see that we added the exponents, right? Let's look at another one. If I had 3 to the second power times 3 to the fourth power, right, I'm going to write it in expanded form, 3 times 3, right, and then 3 times 3 times 3 times 3. Again, here are my 2 factors of 3 for 3 to the second power. Here are my 4 factors of 3 for 3 to the fourth power. And when I multiply them all together, really, that's 2 plus 4. That's a total of 6 factors of 3, which again, if I were to write that as an exponent, would be 3 to the sixth power. Again, look at the expression that I started with and look at the expression that I ended with. Do you see a pattern? Right? You're just adding the exponents, right? These and other similar examples suggest that there's a property for multiplying powers. Okay, so this is where we run into our product of power rules. To multiply two powers that have the same base, so the trick is they have to have the same base, right? These both have a base of 3, these both have a base of 2. So if they have the same base, then you can just add their exponents. For any number a and all integers m and n, right? A to the mth power plus or times a to the nth power is equal to a to the m plus n power, right? So here's a numerical example. If I had a to the fourth times a to the 12th, that's equal to a to the power of 4 plus 12, which would be a to the 16th power. Again, since they have the same base, you add their exponents. Let's look at some expressions that are required for simplification. So here I have 5x to the 7th times x to the 6th. So if I were to go ahead and rewrite this, right, it's just 5 times 1, because that has a constant of 5, that has a constant of 1. And then I have x to the 7th times x to the 6th. So this is just really just using the commutative and associative properties, right? Since all of these things are just being multiplied together, the commutative property tells me I can kind of switch the order of things. And the reason why I put these next to each other is because I can actually multiply these together, right? I know that 5 times 1 is 5, and x to the 7th times x to the 6th, I can use my product of powers rule, right? I know that they both have the same base, so I can add their exponents, which would be 7 plus 6, which is 13. So this would give me 5 times x to the 13th power, or just 5x to the 13th power. Remembering that the exponent is only applied to what it is touching, right? The 13th power does not apply to the 5. If I wanted it to apply to the 5, I would have to put parentheses around both of them. So let's go ahead and do the second one here. So again, same thing. I have 4a b to the 6th times negative 7a squared b to the 3rd. Again, I'm going to use the commutative and associative properties. So 4 times negative 7, a times a squared, b to the 6th times b to the 3rd, right? I'm just basically multiplying the things that are essentially like terms, right? They are things that I can combine together. So I know 4 times negative 7 gives me negative 28. A to the first times a to the second, right? A to this or b to the 6th times b to the 3rd. So again, I add their exponents, and that's going to give me negative 28, a to the 3rd, b to the 9th. So one tricky part here is this, even though you don't see the number 1 there, you know that's a to the first power. So remembering to add 1 plus 2 is really important here. So powers of polynomials. You can also look for a pattern to discover the property of finding the power of a power. So if I had 4 to the second power to the 5th power, and this is why it's called a power to a power, right? Because you have an exponent being applied by another exponent. So really this means I have 5 factors of 4 squared. So I have 4 squared times 4 squared times 4 squared times 4 squared times 4 squared, right? 4 squared times itself 5 times. And again, I can use my product of power rules, right? Where I know they all have the same base, so I can just go ahead and add up all their exponents. So that's going to be 2 plus 2 plus 2 plus 2 plus 2, right? Which is 10. Again, notice a pattern here. I have 4 squared to the 5th power, and I ended up with 4 to the 10th power. So let's look at another problem. If I have z to the 8th to the 3rd power, again, that just means I'm going to have 3 factors of z to the 8th. And again, I can use my product of powers rule because they all have the same base. So I can go ahead and add up their exponents, right? 8 plus 8 plus 8, which I know is 24. So I end up with z to the 24th. Again, do you see a pattern? Z to the 8th to the 3rd and z to the 24th, right? Notice that I am multiplying the exponents, right? 2 times 5 is 10, and 8 times 3 is 24, right? These examples suggest that there is a property for finding the power of a power, and that is known as the power of power rule. To find the power of a power, you multiply the same exponents, as long as, again, as long as they have the same base. So for an example, if I had k to the fifth to the ninth power, again, I could just multiply 5 times 9, which is 45. So that would be k to the 45th power. So now we've learned two rules, right? The product of power rule and the power of power rule. These would be very important ones to write down. So let's see if we can apply these rules. So here I have 3 squared to the power of 3 to the power of 2. So not only do I have a power to a power, I have a power to another power. So let's go ahead and simplify this. So again, I can start with uh, the the power to power. So I know that I can do 2 times 3, right? Because if I have 3 squared to the third power, really that's just 3 squared times 3 squared times 3 squared, which is going to give me 2 times 3, which is 6. So I have 3 to the 6th power. And then now I can apply the last exponent, right? So I have 3 to the 6th to the second power, which again, I can apply my power to power rule and do 6 times 2, which is 12. So I finish with 3 to the 12th power. So again, I just applied my power to power rule twice, right? I applied it to the 2 on the inside, and then I applied it to the 2 on the outside. Let's look for a pattern in the examples below. So here I have xy to the fourth power, and I have 6ab to the third power. So let's look at this first example. So if I were to look at this one, again, I'm going to expand it. I know I have xy to the fourth power, so that means xy times xy times xy times xy. So let's go ahead and take a look at what we can do here, right? I know that I have x times x times x times x. So I have x times itself 4 times. I have y times itself 4 times, right? That's just using the commutative and associative properties, right, to rewrite it. Again, they're all being multiplied, so it's okay if I change the order of things. So basically, I'm multiplying x times itself 4 times. So that's going to give me x to the fourth power. And y times itself 4 times is going to give me y to the fourth power, right? These are like having little exponents of 1 on each one of these. Let's look at the second problem over here. So 6ab to the third power, again, 6ab times 6ab times 6ab, right? 3 factors of 6ab. And then again, using the commutative and associative property, 6 times itself 3 times, a times itself 3 times, b times itself 3 times. Well, that's going to give me 6 to the third, a to the third, b to the third. And I can simplify 6 to the third, right? 6 to the third is going to give me 216. If you didn't know that off the top of your head, that's fine. Calculators are really helpful for calculations like that. And that would be my final simplified answer there. 216, a to the third, b to the third. So these and other similar examples suggest the following property for finding the power of a product, right? So the power of a product would suggest that to find the power of each factor and multiply, right? So if I had negative 2xy to the third power, again, I can apply the power of 3 to each one of those. So negative 2 to the third power, x to the third power, y to the third power. And negative 2 to the third power can be simplified, right? Negative 2 times negative 2 times negative 2 would give me negative 8, x to the third, y to the third. So this would be, again, example of a power of product rule. So whether it's just a number or whether it involves variables, it all is applied in the same manner. So let's look at an example here. It says express the area of a square as a monomial. So here they give us an example of a square here, right? This side has a length of 4ab, and this side has a length of 4ab, right? A square, all the sides are the exact same length. So an area is always equal, right? The area of a square is always equal to the length of the side squared, because length times width, right? So this times this is basically that times itself twice, right? Squared. So it's 4ab squared would be the area of this square. So again, here I have an example of a power of product rule that I can use, right? 4ab squared would be 4ab times 4ab, which would mean that I have 4 squared times a squared times b squared. I can do 4 squared, right? 4 squared is 4 times 4, which is 16. So my simplified answer would be 16a squared b squared. So that would be my simplified answer for that problem. The properties can be used in combination to simplify more complex expressions involving exponents. So when simplifying monomial expressions, to simplify an expression involving monomials, write an equivalent expression in which each base appears exactly only once, right? There are no powers of powers anymore, and all fractions are in simplest form. So let's look at this problem. This one might look kind of scary and complex, but when I think about just applying the rules of exponents, I can go ahead and simplify this problem one step at a time. So let's look at this first part, right? I can go ahead and apply the exponent rules, right? So I can apply this first exponent. I have a power to power here, right? I have negative 6y squared to the third power. So power to power, 2 times 3 is 6. So that's one step that I've made closer to simplifying, right? I use the power to power rule. The next thing I would do is use the product of power rule, right? So I'm going to go ahead and apply the exponents. So I have 1/3 squared x squared y to the fourth squared, right? I applied this exponent here. And then I'm going to apply this exponent here. So I have negative 6 to the sixth power and y to the sixth power. So now I've utilized all of my exponents on the outside here. And then I can go ahead and simplify this another step closer, right? 1/3 squared is 1/3 times 1/3, which is 1/9. X squared is obviously just x squared. Y to the fourth squared, right? That's a power to power rule. So 4 times 2 is 8. So that's y to the eighth. The negative 6 to the sixth power, you're probably going to have to get a calculator for that. That's going to give me positive 46,656 because I'm doing negative 6 times 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 negative 6. Whew, that's a mouthful. And then y to the 6 to the sixth power. And then again, I'm going to rewrite this in a more simplified way. 1/9 times the number 46,656. And then I have x squared, and then I have y to the eighth, y to the sixth. So here I know these y terms, y to the eighth times y to the sixth. I know I can combine those. I can multiply those together. And I know 1/9 I can multiply with 46,656. So when I do that, that's going to give me 5,184. X squared stays the same. And y to the eighth times y to the sixth is y to the 14th. All right. Thank you guys for watching. Let me know if you guys have any questions.